All right, so the first thing I want to do is go ahead and talk about the pacing for the rest of the semester. I mentioned this just a second ago. I want to go ahead and make sure it gets captured in the recording. This week we're finishing up chapter 5. Next week we have a review and a test. However, we also have our optional final. And we haven't talked about the final in a while because number one, it's optional. And number two, traditionally we would have had a paper and pencil test, some time to review in class, but with having an unexpected week out and then transitioning to online, it will be an online optional final on WebAssign that will be available to you next week, probably midweek next week, because what I want to happen is you to finish test 4 and then assess whether you want to take the final or not. If you don't want to take the final, then you're done after test 4 and WebAssign. We'll make sure we have all of that kind of wrapped up in terms of what we need to do this week and then next week to finish it all. But if you want to take that optional final, then I will have some preparing materials as far as list of topics and stuff that I'll release to you. But I won't plan to necessarily make any part of that mandatory. So it will all be optional as far as the study guide, going over any review questions, and then taking that final. Also, just for everybody watching later, if you take the optional final and don't do better than any of your tests, it doesn't count against you or doesn't take off. So it's an option for everyone to take it and try it. It can only improve your grade. But again, if you're happy with your grade, you don't have to do that. So more on that to come as we finish up Unit 5 later this week. But let's go ahead and start off with any questions that you guys have, either from the identities or from the equations. So you guys can drop a question into the chat box if you have one, or unmute yourself. I'm going to make sure I can see my chats here. Sorry, guys. All right, so I'll give you a second there. Okay, one other thing. For some reason, my chat box has disappeared. If you don't have a question, just type in a no question so I can see where my chat box went, and then make sure it's ready to go. For some reason, it has disappeared off my screen, and oh, there we go. It's blinking. It doesn't show me unless I have one. Okay, so I see a no question. A few people trying to get their WebAssign up. So let's take a look. I'll give you a second to get that up and going. And then maybe what we'll do is, if you have WebAssign questions that you want to go over, since we don't have those up, then I'll take questions again at the beginning of our part 2 after our break. So let's go ahead and we'll get started for today and then round back to those WebAssign questions, because it looks like Cole may have one if those WebAssigns are pulling up. And we also have someone else joining us. So let me make sure we get, I think Kaylee is joining us. We'll get her in and then we'll get going. Sorry guys, I'm waiting there, waiting for our 5th person to pop in, and all of a sudden it's just not doing anything. There we go. Sometimes Zoom is a little bit slow. Make sure I didn't close anybody out. All right, so no questions so far, but again, we'll save a little bit of time to take some of those either at the end today or at the midpoint. But let's go ahead and talk about what we want to cover today. So today we are going to be in section 5.4. And I want to show you guys a few things on your Blackboard page to start. So I'm going to go ahead and pull up Blackboard. I'm going to stop the share and show you guys the resource that you most likely either want to print or have handy for your WebAssign. Here, I'm going to pull up another Blackboard to share with you guys. Okay, sorry, this is a little bit slow. You guys should be seeing the Blackboard in a second. We'll move that up so we can see it a little better. So I'm going to click into our folder and just show you guys a little bit in the course content. So far I've been posting everything in your assignments tab. And in the course content are those screenshots from your textbook. And for some of these, in particular, 5.4 and 5.5 are excellent places to just print out those screenshots or write down those formulas. So in section 5.4, we're going to be tackling sum and difference formulas. We're going to try to see how they work is going to be our primary purpose. We're not going to investigate necessarily why they work, if that makes sense. And then we're going to look at more formulas with multiple angles. We're going to look at double angles and a little bit of half angles. We will not necessarily cover all of section 5.5. You can see a lot of these objectives have just been taken off. So we're going to kind of streamline that one. But section 5.4 and section 5.5 are very formula heavy. When we click into 5.4, we're going to see a box of formulas. And these are the formulas that we're going to need to be able to reference and apply. So right now, let's just take a look at them and I'll tell you which ones maybe are the most important. First of all, do you need to memorize them? No. You need to be aware that they exist, how to use them, and why you would use them. Then if you ever needed them, you would need to know that they are sum and difference trig formulas, essentially. So here's what they tell us. Sum and difference trig formulas are going to allow us to look at sums inside our argument, or if we have differences inside our argument. So why we might want to do this is not clear yet, but it tells us we can break up sine of u plus v using sine and cosine of just the u and v. So again, we'll address the y in a second, but sine of u minus v, we've got a formula. Cosine of u plus v, cosine of u minus v. Now, when we look at section 5.5 and we look at our double angle formulas, we're going to reference these guys. But again, as far as memorizing these, especially like tangent, sorry guys, didn't have my phone on silent there. I don't have these books. Sorry, I don't know if you guys heard that one ring too on the laptop. Sorry about that. So I don't expect you to memorize these. And really, when we look at the importance, I want you to focus on the sine and cosine. You have a couple ones in your homework where they just ask you to put in the formula for tangent, but we're not going to do a whole lot with tangent. Focus on sine and cosine. So let's go ahead and I'm going to stop the share the iPad screen and try to take a look at why do we even want to know this? What does this help us with? So hopefully it'll pop up here in a second. Sum and difference formulas. So what it allows us to do is if we understand how to tackle cosine of u plus v or sine of u plus v, if I can represent something new in terms of a sum, or we could also do a difference of something I already know, keeping in mind we could do sum or difference either place, then that allows me to find new trig functions. So let's give an example of this. We know the following. And let's think in radians, and then we'll switch over to degrees a little bit for our Desmos activity. But if I told you, tell me the cosine of pi over 4, you guys could do it. You could say square root of 2 over 2. You could do things like cosine of pi over 6, pi over 3, 2 pi over 3, sine of any of those angles, right? But what if I ask you something like, let me put not yet, right? Because we're almost there. Something like cosine of pi over 8, or maybe something like cosine 7 pi over 12. Now, of course, we could type these into Desmos and get a good approximation. We know sine and cosine both are going to have output values between -1 and 1. We could look at where that angle is on a unit circle, look at our quadrant, and get a pretty good estimate. But we can't actually find the value, the exact value from our unit circle at this point. These sum and difference formulas allow us one way, it's not the only way, to go in and pull out those exact formulas. And here's how we would do it. We would need to figure out how to represent something like pi over 8 or 7 pi over 12 as a sum or a difference of two things we already know. If we can do that, we can utilize the formula. So let's take a look at using this formula, what it says, what it doesn't say, and then we'll calculate an exact trig value for a new angle that we haven't done yet. So let's focus just for a second on the sum for the sine. So if we have the sine of u plus v, our formula says, first of all, it's a plus, but it's going to be sine of u times cosine of v. And then depending on different textbooks, ours is going to pick up with the letter that we just did, or excuse me, pick up with the order that we just did here. So cosine of u, sine of v. Now, how do I remember it? If I'm looking at these, I remember I have sine and cosine, and I'm always going to do, if I look at these parts, sine and cosine of both, but one in each. And then I'm going to have the other trig function with the other letter. Okay, so sine u, cosine v, cosine u, and then just have sine v. Now, we haven't illustrated how to work it, but I want to illustrate why you need something a little bit more complicated. In other words, why not this? In other words, we might have guessed before we saw these formulas that sine of u plus v is sine of u plus sine of v. And this turns out not to be true, right? But we want to know why not, right? So this is an interesting part where we can say, hey, the sine of the sum is not the same as the sum of the sines. Now, that's a mouthful. I'll say it again. The sine of the sums is not the same as the sum of the sines. It means that you can't just decide to break it up however you want to. Now, we know this in other cases. For example, hopefully, if I give you something like the square root of x squared minus 9, you know from algebra classes that you can't just make this x minus 3. It doesn't work like that, right? Because this is actually difference of squares. It factors x plus 3, x minus 3. It's not just two copies of x minus 3. So you can't break up your square root with addition and subtraction. Sine and cosine work very similarly. You can't just break them up and go from there. We have this formula that tells us how you take a sum and a difference and break it up. And it's more complicated than just looking at each component. So if I wanted to illustrate why you can't do this, let's take a look at two particular angles. Let's say we just look at pi over 4, and we just, for simplicity, make our v pi over 4. So if you do pi over 4 plus pi over 4, that's our u plus v. That's 2 pi over 4 or pi over 2. Now, take a look at what you would get if you evaluated the sine of u plus v. In this case, the sine of u plus v, or the sine of pi over 2, is going to be 1. Versus, let's take a look at what happens if you were to just say, I want to try to break it up and do sine of pi over 4, sine of u, plus sine of v. We know the sine of pi over 4 is square root of 2 over 2. So we have 2 square root of 2 over 2, 2 copies. So if I add those two exact values together, I get square root of 2. So splitting up and adding two pieces gave me square root of 2. Adding the two arguments together, the two angles together, and then doing the sign gave me 1. It doesn't work to just break them apart, right? We can do many other examples and illustrate that. Put a big, we will do a big green. No, green is not a good color for that. Gray. This does not work. So if we want to figure out what does work, we've got to go back to the more complicated formula. Let's take this idea, the pi over 4s, and build off of it. If we looked at pi over 4 and pi over 4, we can figure out how to get pi over 2 and sine of pi over 2, cosine of pi over 2 from the formula. But we already know sine and cosine of pi over 2. In other words, trying to use those doesn't really help us out. However, what if I said something like, I want you to think about, let's make this darker, cosine of pi over 12. Or if we switch over to degrees, pi over 6 is our 30 degrees. So we're really talking about 15 degrees. Now, if I think about my unit circle, I know that 15 degrees is my first quadrant. Let's see, there's 45, 15, maybe roughly here. Since my cosine is tracking my x value, it's going to be fairly close to 1, but I don't know the exact value. However, what this says is, if I can figure out some way to represent 15 as a sum or as a difference, using the trig values I do have exact values for, then I'm going to be good to go. So I want you to brainstorm for a minute and think about the angles that you know. We know things for 0, in degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and then we could continue to add our 30s, 45s, 60s, and 90s to go all the way around. So if we look at these, do we have any combination that gives us 15, either plus or minus? You might not be sure exactly at this point what I'm asking you. However, we do, right? And let me show you what it looks like. If I take, let's see, 60 and 45, if I subtract those two, I get 15. Or if you think about 45 minus 30, I get 15. So what this is telling me is that I can go through and think about cosine of 15 as cosine, let's do the 45 minus 30. You could do it the other way. 45 degrees minus 30 degrees. Then if I can utilize my sum or difference formula on this guy, I can find the exact value. So let's do it, and then we'll take some questions. So let's think about this cosine 45 minus 30. And we can also think about the sine. Now, I started with cosine just on our previous slide, but either one would have been fine, right? So it's kind of going to be a similar process. So let's illustrate how to use our cosine addition formula. So in this case, I said addition, but it's actually subtraction. If you look at your cosine of u minus v, we can see that our u is going to be 45, our v is going to be 30. And look back at your formula. Either have that bookmarked or I'm going to copy it again. So cosine of u minus v is cosine of u cosine of v. Notice these ones are different than the sines. On the cosine ones, you're going to have cosine of both first. And then for the minus, it's going to have a plus. The one that's plus has a minus, so alternate signs. And then you're going to have sine u and sine v. Again, don't stress about getting these right. I'll either let you use a note card or maybe a larger formula sheet since we have more this time, and that will be perfectly fine for test 4. I would give you those on our paper and pencil test as well. So let's take a look at what this says. Here, 45, it's going to be my 30. What it tells us to do is plug in cosine of 45 degrees, cosine of 30 degrees, sine of 45 degrees times the sine of 30 degrees. So here's what I want you to do. I want you to take a minute and use your unit circle, or if you need to use Desmos to double check your exact values, do that. But I want you to plug in the exact values, and then we'll simplify together in just a second. All right, I don't know if you guys hear the extra noise. We had a loud noise upstairs. I'm in the basement down here. I don't know how much that comes through, but my littlest one is up there with childcare. So let's take a look at plugging these in. If we look at cosine of 45 degrees, I've got square root of 2 over 2. Then cosine of my 30 degrees, that's going to be square root of 3 over 2. Sine of 45. Oh, hey, Harrison. Hey, buddy, you got to sit over there for a little bit, okay? You can wave to everybody and then head back.
Bye bye.
Okay, so, and then our sine of 30 degrees is going to be our 1/2. Now, what's the biggest thing that can go wrong? Putting these in the wrong place and then just mixing up your formula. We're going to make sure we double check on Desmos so we know if we get it right. But clean this up a little bit. This is a little bit nasty because we're not only having to do fraction multiplication, but we're having to think about our radicals. So fractions, multiply your bottoms together. Do that first. Multiply your tops together. I'm going to do square root of 2 on this guy. And then square root of 2 times square root of 3 gives me square root of 6. So only thing I could really do to put this together is to write it with a common denominator. I could write this as square root of 6 plus square root of 2 over 4. Now, keep in mind, we just illustrated a few minutes ago that you can't do like break a square root apart with subtraction. So that's not the same thing as x minus 3. It's the same idea. If I have these two square roots, I can't just add them together and say it's the square root of 8. It doesn't work like that. And there's nothing else I can really do to simplify this. So what we have just added to our repertoire is that the cosine, notice we were calculating the cosine of 15 degrees, or radians, we could say pi over 12, is going to be square root of 6, the square root of 2 over 4. Now, let's just go to Desmos for a minute, and I'm going to stop the share my Desmos page, because what we want to do is make sure that we can check these answers. And when we calculate an exact value, if we need it, then we make sure it's the right thing. So let's pop over, back over to Blackboard here. And if I ask Desmos, hey Desmos, tell me the cosine of pi over 12. It gives me this value. Let's go ahead and do square root of 6 plus the square root 2 all over 4. You notice we're getting the same thing. So this illustrates how to do it just for one. We have one exact value. Now let's think about, first of all, some questions, and then we are going to go back and think about, sorry guys, we're going to think about sine, right? If we can do cosine, we should be able to apply for the sine formula, and it should be very similar. So questions here. Okay, so let's go ahead and calculate the exact value for the sine of pi over 12, or in this case, 15 degrees. Now, keep in mind that if we know the cosine, which we do, then we should be able to do Pythagorean theorem with the sine. But I don't really want to do Pythagorean theorem necessarily from what I just did. Okay, in other words, I don't want to necessarily do Pythagorean theorem with this. It's a possibility, but I want to show you and make sure you can use the sine formula. So let me go ahead and share the iPad screen. And we're going to calculate the sine of pi over 12 or the sine of 15 degrees. So let's deal with the degrees. And what we want to do, again, is think about how to represent this as 45 minus 30. Or if I could think about it as a sum, that would work too. Now the sum is a little bit difficult in this case because we don't have anything less than 30 degrees that we know the exact value for except 0, and that doesn't help us. So we're kind of stuck with the subtraction. So in this case, I've got my u, I've got my v, and what we need to do is look at the formula for sine of u minus v. So look back at your formula. You've got sine of u, cosine v, and then for these sums and differences for the sine, they match what you did here, whereas the cosine, they're alternating. So we're going to do sine u cosine v minus cosine u sine v. So again, biggest thing that happens is just mixing things up, putting them in the wrong place. And let's go ahead and plug in. So we're going to say the sine of 45 degrees minus 30 degrees, 15 degrees, is going to be the sine of 45 degrees, the cosine of 30 degrees, minus the cosine of 45 degrees, and squeeze that in here, times the sine of our 30 degrees. Okay, so should I give a little more space there? I'm going to go ahead and write 15 degrees. I'm going to put that back together. And then let's plug in. We know square root of 2 over 2. And then thinking about what we did before, we know the cosine of 30 degrees still. And then if we think about square root of 2 over 2 again, sine of 30 degrees is going to be 1/2. Very similar. So we're going to see square root of 6 over 4 minus square root of 2 over 4. So put that together in one fraction, and that should be the exact value. So let's go ahead and I'm going to stop this share and go ahead and share the Desmos screen again. Take a look at checking this. Okay, so if I type in the exact answer, keep in mind you can't just decide to make the top square root of 4, which would give you 2, and then dividing by 4 would give you 1/2. That doesn't work. Notice we're also seeing a pretty small value. Notice if the cosine is large, that means we're very close to the x-axis, and the sine is going to be small. So if I type in sine, here I'm still in radian mode, so pi over 12, I get that same value. So how does this help us out? Well, essentially, now if we know sine and cosine of 15 degrees, I can use my symmetry to split everything up. Instead of in 30-degree increments or pi over 6, I can split them up in pi over 12. That's going to be one of the things we do in the first Desmos activity. So I'm going to show you guys that really quickly and get you going on that part. And then when we come back after our break, we're going to do some more technical pieces. So I'm going to open up the Desmos part here. C underneath. Hopefully that goes the right place. Oh, that's not what I wanted. Sorry guys, I can't see in my typing bar. There we go. Okay, and I'm gonna show you guys the sum difference code. So here's your class code. Should pull up in a second. And I'll link this in Blackboard, so if you're watching after, it should be there. But we're gonna investigate the symmetry and fill out the rest of our unit circle for the 15-degree increments. Okay, let's see. So I had a question. So the final answer, cosine of 15 degrees is square root of 6 plus square root of 2 over 4. And then, yes, that's correct. And then for sine of 15 degrees, square root of 6 minus square root of 2 over 4. Those are considered the exact answers. So they're not as short as 1/2 or square root of 3 over 2, but they are the only exact way to express those values. Now the decimal approximations, like the 0.96 and the 0.25 that we saw a few minutes ago, let's see, these guys, 0.26, 0.97 if I round correctly, those are the decimal approximations, but these two are my exact values. So if you had a question on the test, for example, find the exact value of the sine of 15 degrees. The sine of 15 degrees in exact value would be this one, right? And the cosine would be this guy. Now, are you necessarily going to see the questions like that? No, but they're pretty close, because when we get into this sum and difference on Desmos, we're going to investigate. I'll go ahead and do the teacher slides and show you guys what we're going to get into. You're going to think about sums and differences. So for example, these two look like a sum and a difference, a division, and something that's kind of plain, right? We might be able to figure out which one doesn't belong, right? I'll let you guys think about that. But we're then going to transition to think about how to create one angle from another. So for example, if I think about all of these angles, these are the special angles that we've studied so far. If I add and subtract, for example, if I subtract these two, I could get 15. So let's take a look at 55. Any way we could get 55 out of these? Not just by addition and subtraction, right? If you were able to like divide and then add back, maybe, but not just straight addition and subtraction. So some of these, like 75, 30 plus 45. And we will want to go through our list and see how many I could get, and then which ones I can't get. Right? There's lots I can't get that aren't even listed here. You can get 72. In fact, we're not going to investigate how to get exact values for every single possibility, only the important multiples. So what we're going to focus on in the Desmos activity is they're going to have you go through the 15 degrees again. So the idea here is kind of what I showed you to do by hand, and it's going to have you think about your A and your B, and then it's going to have you walk through those steps. So hopefully what you just wrote down will be handy in matching this up. Notice they work it out for cosine, and then you'll have to look back at the sine. So these values allow you to go in, I think mine is zoomed out here, and think about the unit circle and all the values you don't know. For example, here's our 15 degrees, 30, 45, 60. We already knew 30, 45, and 60, but we didn't have 75. But if you have this guy, think about your symmetry. Flipping through your y equals x should allow you to flip those coordinates and figure that guy out. If you know your first quadrant, you can figure in your second and third. So that allows you to figure out all the special degrees of the unit circle in 15-degree increments. Now, are they going to be pretty? No, they're going to look like this. So what I would like to do is let's go ahead and we'll take, in this case, a 15-minute break, just so that you guys can get into this. And I'd like for you to try getting through slide 5 to fill in the rest of the coordinates for the unit circle for the 15-degree increments. I also have that I'll share later kind of a fillable unit circle with the 15 degrees that you can print out and use instead of just the 30, 60, 90 ones and 45s that we've done. So let's go ahead and stop. When we come back, we'll take questions on this part of the activity, any other questions we have from WebAssign, and then pick back up. I know this was a little bit more technical with our square roots for this one, so thank you guys for sticking with me, and I will see you in just a few minutes. I'll put the Desmos link up just a few minutes before 10:50, and then you'll be able to click back in. So I'll stop my share in my meeting, and then I will see you guys in a couple minutes.